Hello, my name is Andrew Heath and my partner is Caroline McAnder, and today I'm going to be demonstrating our ball balancing robot project for our feedback controls class in fall of 2025. So the purpose of our project was to develop a closed loop system, and for our project we decided to create a ball balancing robot which implements two different PID algorithms, one for the X and one for the Y axis, to balance the ball on the platform so that it stays relatively close to the center. For the hardware on the project, majority of the parts were 3D printed. So as you can see, these linkages, these were all 3D printed, this platform 3D printed, these clips, the base, which the motors would screw into, and then the circuit box, which the base screws into. All of that was 3D printed, and we used a Adafruit touchpad. This is a resistive touch panel. This is used to find the inputs of the robot, of the ball. So for the circuit, we originally planned to use an ESP32 dev module. I can get that out and show that. So we ended up not using the dev module because it just had a lot of issues with the analog pins colliding with the motor drivers. It just wouldn't work well in the code. The motors would turn on, but they wouldn't read any of the step or direction inputs. It just wouldn't do anything. So this is the ESP32 we were originally planning to use. It has, I believe, 4 GPIOs, which is exactly how many the touchscreen needs. But some of the pins had problems with timing in the code, so because of that we couldn't use that for it. So we used this Arduino Mega that I had, which has plenty of analog inputs. If you can see, those are all analog right here, and then these are all digital, and most of these are digital as well. So that gave plenty of pins to use for the project. And so most of this wiring was done fairly recently because I was planning on using the ESP32, and this was pretty last minute, switching to the Arduino, but the wiring still works. It's just not as clean as it could be. So we're using 3 motor drivers. These are the A4998, I believe is what they're called. They allow for 1/16th microstepping. I was originally using that, but I found issues with the motor speeds. Whenever I did that, it would just limit the motor speed to where it wouldn't allow for the motors to react in time for the ball. So I switched to 1/8 microstepping, which, as you can see, those 2 pins with the red wire are connected, which is the MS1 and MS2 pins on the driver, which connecting those does 1/8 microstepping. If you connect all 3, so if you see on line 7, if you connected that one to the other 2 as well, that would be 1/16th microstepping. For the motor drivers, there is a 12-volt input that is ran by this AC to DC power adapter, which is used to power the whole project. It connects to this jack right here. It's just a jack connection, and if you see here, that's just a plus and minus, which connects to this DC buck converter, which converts, I used it to convert the 12 volts to 5 volts, so it could be used with the Arduino. This wasn't exactly necessary. You could have just used a power supply, but this made it easy to just power the whole project with one power supply. And if you put it together, this could be portable as well if you actually use this rather than a whole power supply unit. But yeah, this DC buck converter converts the 12 volt to 5 volt, which feeds to the Arduino, and as well as the VDD pins on the motor drivers, and they all share grounds. And I'm using this switch to turn the whole thing on and off. It works very well. And there are capacitors between the motor voltage and the ground that just protects the motors in case there's any really large voltage spikes for some reason, which more than likely wouldn't happen with something like this, because this is a 12 volt 10 amp power adapter, so it couldn't exceed 12 volts and 10 amps. And each one of these motors, to my knowledge, requires 1.7 amps. So and I think it's 4 volts, but it has plenty of voltage. It's just the amps I was more concerned about, which it has plenty, it works. So with the mechanism here, it's 3 different arms, which are 2 linkages each, with this is a RC, this is an RC tie, which it moves, so you can't, it's hard to tell here. I have these were also 3D printed, these little holders, so this just holds it in the middle right here between. So this is just a screw right here, and these connectors just hold this right in the center right there. But that's a little ball, so this can spin. So this is easier to show. If you just move it like this, they can move in all directions. So yeah, for the ball, I was originally planning on just using a small little bouncy ball, but after testing, this touchscreen could only respond to a certain amount of force, which the bouncy ball wasn't exerting on this. So I found this ball, which does, but obviously compared to the size of the screen, this is pretty large. So my professor gave us this steel ball, which is about the exact same size of the bouncy ball, but gives it enough force to actually balance. So for the motors, we originally planned to use 1 amp motors, which is about half the size of these motors in terms of width. After testing, those motors didn't supply enough torque to keep the platform up. So if you put any amount of force onto the platform, the motor would immediately drop. So obviously that's not good for a ball balancing robot that needs a steel ball, because that just isn't going to hold it. So got these motors instead, and they work really well. So I'm now going to demonstrate the robot in action. So here we go. I'm going to turn the robot on with the switch. So this platform, obviously not very stable. So I'm going to try and hold it best I can, but let's see. Okay, so as you can see, it works for a second. So yeah. So as you can see, the touchpad sends the inputs of the ball to the Arduino, which feeds it through the code, which includes the 2 PID algorithms, which computes the error, which the error in this is the distance from the input to the center of the platform, because the center is where you want the ball to be. So that's the error. the integral term would be the error over time. So however much sampling time it is, which I believe in my code, it's 6 milliseconds. So over that 6 milliseconds, all the inputs added up, that's the integral of the error. Derivative is the instantaneous velocity, which is the, so you take the final position minus the initial position divided by the sample time, I believe. So yeah, it's just right. It's just it's derivative. So rate of change. But as you can see, it works almost, but not entirely. It doesn't keep the ball in there for very long. And what I've spent a lot of time working on the code, trying to figure out what it could possibly be. And after looking at it, I believe that it's because of all the noise in the touchpad. So I'll actually demonstrate this right now to show what I'm kind of referring to, so you can actually kind of see. So, well, this is gonna, okay. So at certain points, you can almost see it. As you can see, I'm moving it around very slightly in this corner. Okay, hold on. That wasn't meant to happen. It's moving it back and forth, even though I'm not really moving it. And it's almost at times, it looks like it's just trying to push the ball off the platform. And I believe that's just because of all the noise that's in this touchpad. So whenever you put it somewhere, it sends more than just one input, which, I mean, that's going to be the case for any touchpad, but this one just seems to have a lot of noise. So there are ways to go against, to get rid of this noise in coding, but I just couldn't figure it out. So it works slightly, but after a couple seconds it fails to balance the ball. And I tuned the PID parameters for a very long time, and after testing for hours, I came to the conclusion that it wasn't the PID parameters, it is something else in the code. So like I said, I believe it's due to the noise. I think that if there was a way to reduce the noise in the code, that it would fix the problem. Another thing I considered was adding some sort of passive filter to get the noise reduced as much as possible without even having to change the code at all. So I would just need to add some sort of passive filter to the wiring, to the circuit. The only issue with that, though, I've found is that this is a 4-pin touchpad, meaning that there's an X plus, an X minus, and a Y plus, and a Y minus. So because of that, these are wired directly to the analog. So these pins, A0 through A3, those are all connected to the touchpad. They're correlating to the X plus, X minus, Y plus, Y minus. And the reason they're analog is because for the touchpad to work, the signals need to flip between high and low very quickly and very frequently, which is best done with an analog input. And also it's a resistive touchpad, which measures resistance in the touchpad, which is more of an analog input than anything else. And the reason that this matters is because if I were to try to add a filter to this, it would cause issues between switching between high and low like that. It would cause a lot of issues in that switching. So I believe that the only way to truly fix the problem would be to adjust the code. So I believe that if we spend more time on this project, we could improve the smoothness by changing the different gains and also figuring out what could possibly be the issues in the code. Because like I said before, I believe that it's due to the noise in the touchpad, but there could be other problems as well. You could have something to do with the motors. These motors aren't the same model, so there could be differences in the acceleration and whatnot. There's really no telling at this point, but I limit it down to either being the touchpad, the motors, or the code, truly. If I were to change this at all to improve the robot, I would probably use a better touchpad than this one. This one's not terrible, it just, I probably would go with something that's not a 4-pin. The platform could be designed a little bit better to reduce vibration. I actually, whenever I printed this, whenever I designed the robot, I forgot to fillet one of the corners, one of these sides. I believe it's this one right here. Yeah, this one right here, this corner. Right here, in between the link and the actual platform, there's a little, so on the other ones, it's filleted right there. Right there, it's just square. So I forgot to fillet that part, and I printed it without seeing that. So that would probably be the first fix I do. And I would probably add better safety. I think that this switch is good, but I probably would have used a different one, something like a button I could have just pressed. Because sometimes this is kind of hard to flick back and forth because it likes to move around. And the main thing I would fix is whatever the problem would be in the code. But yeah, so this is the ball balancing robot. It almost works. You can see it almost working. It just doesn't work perfectly right now, but given time and more effort, I'm sure we could figure out how to get it to work. Thank you for watching this demonstration, and I hope you enjoyed and I hope you learned something.